Now we have everything we need in order to define what our eval function looks like. So we're going to have this eval function. It's going to work on programs of S lines with N inputs and M outputs. And this eval function, what it's going to do is it's going to take an input string, and that input string is going to be the number of bits that's necessary to represent our program. So this was this roughly 4s log s number. And then we have N bits. Those are the N bits of the input. This is saying we need to be given the program. This is saying we need to be given the input to the program. And then the output of this is going to be M bits, because we said there were M output bits. So the number of bits we're getting as input to eval is the number of bits we need to represent an S-line program, plus the number of bits we need to represent an N-bit input, which is just N. And then our output is M, for our M bits of output. So basically what this program is going to do is it's going to say, well, I'm going to assume that the first S of S bits are going to be the program, and then the remaining N bits of the input, those are the inputs to that program. And then our output is going to be the result of running that represented program on the provided input, and then maybe something if there's a compile error. If this is maybe like I referenced a variable before assignment or something like that. So this is what our eval function is going to look like. Let's now actually look at how our eval function is going to behave. So basically, we're going to take the same idea that we used for how your computer executes code, and we're going to do it in this world where we only have integers instead. Since eval kind of has all of these parameters defined, it knows exactly which bits are going to be the program bits, it knows which bits are going to be the input bits, and from those program bits, it can break those up into the triple of integers and so forth. This is the lines of our program, and let's say that our input is 0, 1. For eval, N is 2 and M is 1. So we have 2 inputs and 1 output. The way that we're going to be giving the input to eval is you would just take all of these numbers that you see, all of these integers you see from the lines, convert those to bits, and then concatenate them all together, and then add a 0 and a 1 at the end of that. So that's what eval is going to see when you give it input. So then what we can do is we're going to say, let's take our variables, or we need to figure out what the value for each of these variables is, understanding the last M of them are going to be output variables. We're given 2 input variables, so whatever those 2 bits were after our program, those go in as the values of the first 2 variables. So our inputs were 0 and 1, so variable 0 gets bit 0, gets value 0. Variable 1 gets value 1. Next, what we do is we say, all right, well, variable 2, that's going to get the result of doing a NAND with 0 and 1. So variable 2, we want to do 0 NAND 1. 2 is the result of NANDing 0 and 1. So 0 NAND 1 is 1. The next thing we have is 3, receives the result of doing a NAND with 0 and 2. 2's value is 1, 0's value is 0. So 3 gets the value of 0 NAND 1, which is 1. And then 4 gets the result of doing a NAND on variables 1 with 2. So that's 1 with 1. So 1 NAND 1 is 0. So the value of 4. And then we have 5 receives the result of doing a NAND on variable 3 with variable 4. So that's 1 NAND 0. So this becomes 1. This, by the way, is a representation of XOR. This is that same representation we had a few slides ago. So you can see that this did correctly give us the result of 1 if we're doing an XOR of 0 with 1. This program is written in a representation of a NAND straight line. In the same way that this is a representation of NAND straight line in this Python-like thing, this is a representation of NAND straight line as triples of integers. And what eval is going to do is it's going to take a representation of NAND straight line as a bunch of bits, as this S plus N bits. Let's try to write now some pseudocode for exactly what's going on with this eval function. So what we're going to need, the pieces we're going to need for this eval function. So we need the table that's going to hold the variable values. We're also going to have this function that I'm going to call get. What get does is it takes the table and an index, and it returns the value of the variable of that number. So it gets the table and the number, and it says, here's the value that the variable you numbered has. And then I'm going to have update, where what update does, so kind of like get, we give it the table and an index, but then we're also going to give it a single bit b, so a value b. And what update does is it gives basically a new table that is exactly the same as the old one, except variable i's value has been changed to be equal to b. So the table holds the variables and their values. Get says, here's the value of variable I in that table. Update says, change the value of variable I to be b in the table. And here's your new table. What we're going to be able to do then is we can sort of assemble these together in some pseudocode. We can assemble these pieces together in some pseudocode. Where what we're going to do is we're going to say we have this table t. We have our table t. And I'm going to let little t be the size of it, whatever that is. So what I can do is I can say for each of my inputs, for I in range n, I'm going to update my table so that the value at position I was going to be input I, the ith input. Preload the table with your input values. Preload the first n values of your table with the input values. And then we can look at every single one of our triples in our program. And what we're going to do is our triple ijk says that I gets assigned the NAND of j with k. So that's what our triple meant. The variable numbered I gets assigned the value of variable j with the value of variable k. So what I'm going to do is I'm going to get the value of variable j by looking up j in the table. I'm going to get the value of variable k by looking up k in the table. Then I'm going to say in my table, change the value of I so that it's the result of doing our NAND with those two other values. And then our outputs are just going to be give me the last m bits. First, we're going to load input bits into the table. And then the next thing we're going to do is we're going to say read and write to the table for each of the triples. And then finally, we're going to say return the last m bits. So these are our three steps. We update the table to have all of the inputs in it, and then we get from the table the last two things in each triple, and then update so that the NAND of those goes to the first thing in each triple. And then when we're done, we just return the last things. So this is exactly the same pseudocode that we saw before, exactly the same procedure we saw before, just now in terms of these triples. Yeah. The output is always going to be in the last m bits, yes. So this is something that we've already been doing, is having our outputs must be at the end. So what we're going to do is now we can talk about, we're going to show that we can implement this eval thing using just NAND. So we're going to use that idea of the pseudocode where we're just having this table, we read values from the table, we do NANDs on them, and then write that value to the table over and over and over again. We're going to do that using only NANDs now. The first thing we're going to talk about is get. So basically our table is just, the way that we thought of it before was kind of as a column of bits. Something like this. You can think of this as just a bit string, though. Instead of thinking of these as columns, we're just going to represent them sideways as a linear string. So with get, what we're giving you is I'm giving you the string that represents all of the bits in that table in order so the 0th bit hold the value of variable 0. The first bit was going to represent the value of variable 1, and so forth. The way that get works is I hand you the bit string t and the variable's number I, and it gives us as the result the value of that variable I. Does this look familiar? Yeah. Yeah, so this is basically just lookup. So this is lookup, where what we need to know is how big our index is for lookup. How big is our index for lookup? Yeah. For lookup, our subscript was the size of the index, not the size of the bit string. So the log of the length of t is basically what that would end up being. So in this case, our lookup, if we say that this L right here, this equals the length of each variable, so the number of bits we need to represent each variable, this is lookup sub L. This is the same as doing lookup sub L of t with I. How many gates do we need to do lookup? This was roughly like 2 to the L gates is what we did. To do lookup of k, I could do two lookups of k minus 1 plus an if. And then to do lookup of k minus 1, I could do 2 lookups of k minus 2 for each of those, plus ifs for each. And when we worked this out, we did this proof. We talked 2 classes about this, where we had 2 to the power L. So we know we can do get because it's just lookup described differently. But it's exactly the same as lookup, and the number of gates we need to implement this we know to be 2 to the power L. So the next thing we want to talk about is we want to talk about update. The way that update is going to work is update, we give it the table. This SL, that's the table. We give it the number of lines. We give it the bit that we're going to be changing some index in the table to. And we give as output the new table. Yeah, this should be 2 to the power L. The way that update is supposed to work is we want to change the value of index I in the table to be whatever that bit B was. In this new table that we're giving, every single bit is going to be the same except for one of the bits. So when we compute this new table, when we give the new table, that's going to be exactly the same as the original table, except one bit is going to be different, and that is the bit at index I in this case, where the bit at index I is going to have value B. If value B was what was already there, then it might not be any different. There might be no different bits, but it's going to differ by at most 1 bit. When we do a lookup, we said lookup sub k. The k represented the number of bits that you needed to represent your index into your string. So that means the length of your string was 2 to the k. So here, L represents the number of bits we need to represent our variable, which must have meant the number of variables was roughly 2 to the L. L is the number of bits we need per variable. 2 to the L is going to be the number of variables we have. We have 1 bit per variable. So 2 to the L is roughly the size of the table. When we looked at this pseudocode back here, we have like a for loop. For loops are not something we've talked about how we can do. So we don't know how to do a for loop with NaN straightline yet, but provided that we have kind of only a finite number of iterations in our for loop, we can just sort of unroll that loop. So if we knew in advance how many times we would iterate through that loop, we could just unroll it and just do the stuff explicitly that exact number of times. So instead of saying for I going from 0 up to 4, we could just say 5 times in a row, copy paste the same stuff. So that's essentially what we're going to do in order to mimic this idea of for loops. What we're going to do is we're going to look at each bit in the table, and we're essentially going to say if the index of that bit was the one that I wanted to change, then make it B. Otherwise, leave it whatever it was before. Make it equal to bit B. Otherwise, leave it whatever it was before. So in order to do this, we're going to use this equal function, where it tells me whether or not 2 given bit strings were equal, essentially. And this equal is going to require roughly a linear number of gates. One of your homeworks is to figure out how you can do equal with roughly a linear number of gates in terms of the number of input bits. Looks kind of similar to compare. Essentially what we're going to do in order to do our update is we're going to say for each of the rows in our table, which we said there's roughly 2 to the L of those, we're going to say that if this row is the row we were looking for, so A is going to tell us whether or not I was equal to J. So I says, here's the row we're looking for. J says, here's the row I'm looking at. If the number for the row we're looking for matches the number for the row we're looking at, A is going to be 1. So A indicates whether or not we're looking at the right row. So we're going to say if we're looking at the right row, then we're going to return the value B. Otherwise, we're going to return the same thing that was originally in our table. B was the input to update. B was this input to update that told us what the bit was we were going to change things to. So if the row we're looking for is the row we're looking at, then I'm going to give as my result B. Otherwise, we didn't want to change that row. So in that case, I give whatever was there before and assign that to some new table and then return the new table. So that's the idea. We want to have this for loop where we say for each row in the table, if this was the row I'm looking for, return B. Otherwise, return the old value. And then return whatever that new table is that we just got. And essentially what we can do is instead of doing this as a for loop, we can just have, say, 2 to the L lines where we've done this, copied and pasted over and over and over again. So we do this explicitly where j is equal to 0. So I try this for 0, and then I try this for 1, and then I try this for 2, and then I try it for 3. And I just do it for every single row in the table. So we're just going to have a bunch of these. And now this is going to give us update. So these are now all of the pieces that we need. We know how to do get, because get we said was the same as lookup. We knew that we could do update by this procedure here. And then when we go back and we look at the pseudocode for this, these were the only things that we didn't know how to do. So we can do sort of this for loop by this loop unrolling thing, kind of explicitly. We can do update. We can do get. Here we have update again. We know how to do nan. So all of these are pieces that we know how to do. So through some combination of loop unrolling or using syntactic sugar that we've defined this class or prior, we can do all of these things with nan. Yeah, so right. So in this case, notice how here we basically have this new table. So we're not allowed to reassign the values of variables in our nan straight line. You have to invent a new variable every single time, but we can do that. It didn't make sense to do it there if I actually had for loops, because I can't invent a new name for a thing. But once we unroll that for loop, not a problem anymore. So what we know now is that we can compute any finite function with circuits. We talked about that last time. We can do any finite function with circuits. And in fact, if I wanted to, I could even write a function that evaluates programs of a certain size. So if you told me the size of the programs you wanted me to evaluate, I could write a function that would do that for you. That's what we talked about today. So if we're going to try to use this to actually build computers or something like that, if we want to actually use these ideas in order to actually implement computers, we have these questions about maybe for whatever function you're trying to represent, how expensive is that? I had to tell you how big the program was that I wanted you to be able to simulate. Did I tell you a big enough program? If I have a function, my goal function that I'd like to implement, was my implementation small enough that you could actually evaluate it? This is an important question that you're going to want to ask when you're sort of deciding what it is you want to maybe implement in hardware. How much hardware do you need to achieve the goal function that you really want? Some functions are more expensive than others. Maybe we want to know what is the most expensive function. Can we come up with a guarantee that some function is going to be at least a certain amount of expensive? So maybe if I'm trying to actually implement my eval circuit, what's the size that it should be in order to guarantee that I could get every function that I could implement with my eval, since I had to pick this size? Which says that if I wanted to be able to do every function of a certain number of inputs, how big should my eval be? How many gates does my eval circuit actually require in order to do that? These are all follow-up questions we might want to ask in order to figure out, is this actually going to be an efficient way to compute? We can do any finite function. We can simulate programs of finite functions. Is this actually efficient? We need to be able to answer these questions before we're going to be able to do that. So that's where we're going to pick up next time. We're going to talk about this idea of complexity of functions so that we can start to answer some of those questions.